let's get started with this webinar, How CFD Pushes the Boundaries in Industrial Applications. Welcome. We are very proud to inform you that our guest speaker for this webinar is Professor Dr. I.R. Bert Blokken of Eindhoven University of Technology at Department of the Built Environment, and of course of KU Leuven in Belgium, Department of Civil Engineering, together with Infinite colleague Adrian Baitz. They will be the presenters for this webinar for this afternoon. The duration of this webinar is about 1 hour. And before we get started, you should see something like this in the right upper corner. That's the screenshot of a GoToWebinar introduction. And at the end of the webinar, you will be unmuted. So during the webinar, you are muted. And then I will unmute you all. And then you can unmute yourself. Of course, this webinar will be recorded and sent to you afterwards. So I now would like to hand over to you, Adrian, so that you can explain something about the speakers for today.
Yes, thank you. Can you hear me well?
Yes, we can hear you, Adrian.
Fantastic. Hi, everyone. Welcome to today's webinar. As Erna mentioned, we are very happy to welcome Professor Dr. Engineer Bert Blokken as a guest speaker today. You probably know him as a reference in this domain at Eindhoven University of Technology and KU Leuven in Belgium. As you can see on the slide, his main areas of expertise are urban physics, city and building aerodynamics, and sports aerodynamics, which will be showcased later on during the presentation. I myself, Adrian, work at Infinite. I've been here for 4 years now. I'm an account manager, meaning I'm in contact day in, day out with our customers in the Benelux. Myself mainly in Belgium. So we are very happy to collaborate with research institutes, with industrial companies to work on their simulation applications, such as CFD, which can cover a lot, as you can see. So let me see if I can move to the next slide. Yes. So today's agenda, I will start off with giving you a little introduction about ourselves and about CFD. I will then hand over to Bert for his presentation of today. If you have any questions during the presentation, feel free to drop them in the chat box and we will address them towards the end of the webinar, or you can just wait until the end and just unmute yourself and ask the question right away. So with this, for those of you who may not know Infinite, we are a company based in Benelux. We are part of a larger group, which is called the 4iTego Group. What we do as a group is we support industrial companies, typically in the discrete manufacturing industry, what we will call the maakindustrie in Dutch, so companies developing and manufacturing products. And we help these companies with the digitalization of their product development processes and manufacturing. Within Infinite specifically, we are very focused on high-end engineering simulation, and that can go from structural simulation, fluid simulations, electromagnetic simulations, and more also the coupling between those different types of simulations to actually represent a product digitally, how it will perform in the field. We have a team of more than 60 team members. Around 2/3 of that team is a team of technical consultants who have a lot of experience in the field, and also are day in, day out supporting our customers to tackle the challenges they face within product development, R&D, manufacturing, etc. When we talk about engineering simulation, we mainly work with Ansys technology, as we believe that Ansys is really the gold standard for engineering simulation. First of all, let's say the simulation suite of Ansys is quite extensive. Ansys started as a structural company 50 years ago with a finite element code, but over these 50 years has really developed itself to a comprehensive engineering simulation solution. I was mentioning it before. Fluid analysis with CFD, which is the topic of today, but way beyond that, electromagnetics simulation, optics simulation, semiconductors, yeah, you name it. And in all of those areas, either through organic growth or through acquisitions to complete our product portfolio, you see that accuracy of the simulations and high standards of simulations is something that is very central to all the solutions that we support. Next to that, we also aim to be a value partner, an advice partner. I was mentioning it before. 2/3 of our team is composed of technical consultants. Even all of our commercial colleagues have a technical or engineering background. And that's because we really need to understand the challenges that our customers are facing so that we can help them properly. Above that, you see that Ansys is also an open ecosystem. We don't really require a specific stack of technology to be able to work with. We appreciate that, well, you know, companies are using different technology stacks, really aiming to be compatible with all of those, and some strategic partnerships are in place to make those workflows even better. For instance, with PTC. So when you think of simulation, and that will be, I think, a recurring theme today. In the past, simulation was maybe seen as something that you would do at the very end of the development of a product, or something that would be only dealt by, you know, a couple of people with a very solid background in that specific domain. Whereas you see that today, simulation is being used more widely in the product development process. So it really starts at the ideation phase with some, let's say, mid-end simulation technology that allows engineers to already understand how a product will perform, even if it's still in an ideation phase, which basically helps to develop products better earlier in the process. Typically, if you would do a simulation at the very end and see that something is wrong or you need to change something, typically the cost of that change will be very high because you've maybe already spent some weeks developing it, or maybe if you've already built a prototype. So simulation can really give some insights earlier on that you might not have before. Also towards the operation of a product, when a product is already manufactured and is in service, you see that more and more companies are leveraging analytics with measurement data, with sensor data, to be able to use that data from the field to couple it back actually to their simulation models to predict how the actual product will also perform in the field. So when you think of Ansys and the technology it provides, I was already mentioning it before, towards the bottom left you see structures. That's where it all started with a finite element code. Now it has really expanded to all those different types of physics and all different types of applications. You see some of them at the top. Some of the, let's say the big industry trends that we are seeing today, for instance, electrification, autonomy, which can be autonomous vehicles, but also a lot of other things like drones, for instance, or off-highway vehicles or agricultural machines. All these applications require a digital model that really captures how the product will perform in the field. And to be able to do that, you need to capture all those different aspects, all those different physics, and that's where Ansys really stands strong. And on top of that, you see a layer called simulation platform. That's really where we want to bring everything together. You're being able to apply, for instance, the materials that are used, a couple different types of physics together, build workflows inside a company so that, for instance, a team of design engineers can also communicate very well with a team of simulation engineers, and so that we don't have any loss of data, and make sure those processes are optimized, which is also very important for industrial companies. So that's a bit the general part, let's say. I'm struggling to get to the next slide. There it is. Now zooming into the second tile, which is CFD, and I guess most of you know what CFD is, but maybe bringing it back to the basics. CFD stands for Computational Fluid Dynamics, and is basically the science of predicting, you see it on the slide, fluid flow, heat and mass transfers, chemical reactions, on these kinds of phenomena. We do that with computer simulations, with software, and basically with these types of simulations, what you're actually doing is solving a set of equations, which can be conservation of mass, second law of Newton, conservation of energy, etc. And with that, you can tackle a whole type of applications. As you can see on the left, CFD is typically used to provide more insights into some phenomena that you want to understand of your product, of your applications, which can be a pressure distribution, a velocity distribution, temperatures, heat transfer, or the second bullet point that you can see here, forces like lift and drag, the typical example of the Formula One car, and I guess the people from the solar team which are in the call, they know everything about this. Distribution of multiple phases when you are dealing with applications that are multi-phase, and also there CFD can play an important role. And then also looking into more chemical reactions, combustion processes, for instance, in the process industry, CFD is used a lot to understand how these reactions take place. And for instance, if you're emitting pollutants or how you need to capture those pollutants. So CFD, I was mentioning at the beginning of the presentation, is not only used at the very end of a design to validate it, but it's being used more and more in all the different stages of the engineering process, of the product development process. So conceptual studies, the detailed analysis, as it has always been done more traditionally, but also optimization studies, what-if studies, if you want to change some parameters, you want to do some studies without building a prototype. And also if you already have a product that is in the field and is not operating how you expect it would operate, or you are seeing some weird things you don't understand, also there CFD can help you to do some troubleshooting. So overall, you see that CFD can be used as kind of a virtual prototyping technique, and it will typically complement the actual testing and validation that you would do with a physical prototype. I think an additional advantage of CFD is that you can also measure things that would be very difficult to measure in real life. You cannot put a sensor on everywhere, depending on the application. Sometimes it's very difficult to measure some things. With CFD, you can typically do that. Look into your model and look at different values and different physics aspects. So this is a really, it's a broad range of applications, and here at Infinite and with Ansys, we work together with a lot of research institutes and industrial companies developing products here in the Benelux for a whole type of very wide range of applications, like for instance, cooling of battery packs, or in turbo machinery, how to efficiently design a pump, and how to make it as efficient as possible to avoid cavitation, for example, or looking at heat flow in all type of industrial applications, or looking at temperature control in some applications or products where a constant temperature is very important. A lot of different applications, as you see, that we are very happy to to collaborate with our customers and collaborate with that with our CFD team. So with that, I'm gonna pass the word to our guest speaker of today, who will also explain you a little bit more about some of these industrial use cases where CFD might be of benefit. So I now,
yeah, I can manage.
Yeah.
Thank you.
Yeah, you're welcome.
Okay, yeah, welcome everybody. Well, this is a bit an unusual start slide, but when making this presentation, I remembered my first presentation ever at high school, and we were 16 years old and had to make a presentation, not PowerPoint, of course, but that's a longer time ago. And my presentation was about Belgian beers, and today in the presentation I also want to say something about Belgian beers. So how CFD pushes the boundaries in industrial applications. Adrian and Erna have been so nice to give an introduction, so I will not spend a lot of time to introduce myself. So I studied civil engineering at KU Leuven. I did also my PhD in civil engineering, building physics, and after a postdoc in Montreal, I applied for a job at Eindhoven University of Technology, where I've been working now, I think, almost 16 years, and still happy to work there. And I'm also now part-time working at KU Leuven. And actually, the objective of this presentation, it's also the question I got, is to tell something about the power of computer simulation for a wide range of applications. What I would also like to demonstrate is that although scale adaptive approaches are intrinsically superior to steady runs, that is steady runs and sometimes unsteady runs is still the most applied method. And I'll have a list of applications that I'll run through together with you, starting from the ventilation system for a Duvel beer brewery and then ending up with some cycling applications. So the ones you see here in blue are performed with scale adaptive simulations, while or scale resolving simulations, sorry, and the ones in black are performed with RAN simulations. I would like to start with a quote here, and I think this is a very nice one. How can it be that mathematics, being after all a product of human thought independent of experience, is so widely adapted to the objects of reality? And that's really true, huh? Because mathematics is something that was invented by us, by people, and it's surprisingly accurate often to predict real things. That I often tell my students that this is one of the most beautiful things they will probably ever see. These are the Navier-Stokes equations. They fit on one slide. Okay, it's a simplified form because this is for an isotopic homogeneous Newtonian fluid, but nevertheless, these equations can predict a wide variety of fluid flow processes, whether it's about the air in your respiratory system, or it's wind flow around buildings, or the flow of blood in your veins, can all be predicted by these equations, just fitting miraculously almost on a single slide. Okay, let's look at some applications. This was the first one, was a study actually that we did a while ago, and as many of you probably know, beer is brewed in several processes, and you have fermentation tanks, and CO2 is generated. And CO2, as you know, is more heavy than air, and CO2 concentrations actually can get so high that the situation can become dangerous. So what you see here is the floor plan of a building with in red the fermentation tanks, and we were actually asked with CFD to assist the design of a new ventilation system in this existing building. And initially it was thought to have a displacement ventilation system with inlets shown here in yellow near the floor and the outlets near the ceiling. So simulations were made here, and nothing too fancy. Steady run simulations with SDK omega model with proper boundary conditions in terms of heat generation and CO2 flux. And specific conditions were analyzed, different temperatures, also different inlet velocities, of course, resulting in different ventilation flow rates. And I'll directly go to some of the results. This is a vertical cross-section. You see the two fermentation tanks, and you see the concentration of CO2 indicated by the colors. Here you have to take into account that if you get a green color, this is about a 0.1 mass fraction. So that's 100,000 ppm CO2, and that is considered as life-threatening. And even though we are, well, many, I think, of us appreciate this particular beer, of course, the brewing process should be safe and should be healthy for people working there. So this is would not be a good ventilation system, and of course, knowing that CO2 is heavier than air, and this is not surprising that with this kind of ventilation system, you cannot really expel the CO2 properly out of this room. Another case, this is the reverse, also displacement ventilation, but from the ceiling down to the floor, which makes more sense here, given the density of CO2. And this is an extreme case where we would be able to have very large inlet planes. Very difficult to achieve that in reality, but let's just look how far we could get here. Again, looking at different configurations, different inlet velocities, flow rates, and so on. So here you get actually the opposite situation. Here you get very low concentrations. But this, as I said before, is not really a feasible approach to design ventilation inlets. So finally, we ended up, after a bit of optimization, with this kind of configuration of inlets at the ceiling and outlets at the floor. And that, again, with similar types of simulations, with the different boundary conditions, that gave a rather okay view, as you can see here. Still, at some locations, concentrations will be a bit too high. And then actually the idea is to turn up the ventilation depending indeed on local concentration measurements. So this is actually an illustration, a simple illustration of ventilation, but then in a rather peculiar and specific case. Other application, larger scale, is cruise ships in the Rotterdam cruise terminal. So yeah, this cruise terminal is actually quite famous. So it's from the Holland-America line, where many European immigrants actually moved to the US. And this is an old photograph of what this terminal looked like. And with the cruise ships of that time, they were not that large as now, this is an indication of where the cruise terminal is. So you can see it here at the top left figure. So this is the Maasvlakte in Rotterdam. And then you have the cruise terminal further inland. So at this location here, so zoom in here, and here you see actually a much larger ship being moored at the quay. And that is actually the same cruise terminal, but yeah, how it developed over time, and now there are high-rise buildings there. And these cruise ships have become much larger. And you can see that also here, and this is a comparison between the Titanic, which was one of the biggest ships at the time, and a contemporary cruise ship, Oasis of the Seas. So you can fit quite some Titanics in this new cruise ship. But larger ships also means more windage area, so larger wind forces on the ships. If you then have this ship at the cruise terminal where there's also high-rise buildings, the high-rise buildings also influence the flow. So the high-rise buildings will have an effect on the cruise ship, the forces on the cruise ship, and vice versa. So this can be an issue, and that's why actually we did simulations of this whole cruise terminal area. You see the computational grid here on the right side. Also the ship was included, and for other simulations it was excluded, to really see the effect that the presence of the ship would have on the buildings present there, and also on wind speed at pedestrian level. And also here steady run simulations were employed that were validated with wind tunnel measurements of forces on the ship, and also field measurements on the cruise terminal itself of wind velocity and turbulence. And then finally, for different wind directions, we could predict what the resulting velocity fields were, but more importantly, what the forces were on the ships. And here you see the pressure coefficient, mean pressure coefficient on the different faces of the ship. And this has allowed us to determine the the number and the position of the mooring cables to have this ship safely in this cruise terminal. Because I think, as you know, regularly there are accidents with cruise ships, with container ships, either near ports or in narrow canals. I remember the Ever Given situation in the Suez Canal, and unfortunately these are not such rare occasions, so that's why this kind of studies can be important. An article was written about that. If you want more information, you can find it there. Then air pollution is also an important problem. This was a collaboration also between different partners focusing on particulate matter. And here you see on the right side a very nice drawing of the Environmental Protection Agency in the US that compares actually the size of a sand grain or sand grains with the size of a human hair, and then the size of particles, the largest fraction of particles of PM10 in blue and PM2.5 in red. So you see these are very small particles, usually invisible by the naked eye, and we characterize them by an indication PM, particulate matter, within the number, and PM10 means that's all particles with a diameter equal or smaller than 10 micrometer. So you have particulate matter, finer particulate matter, and then the PM1 is even finer. So what is the problem here? That if we inhale these particles, well, PM10 has been around as long as the planet exists, and you get PM10 from dust storms and sea spray and so on. And the human respiratory system has evolved over the past many centuries to expel these systems, and so expel these particles, and so your respiratory system will take care of that. But due to human activities, think about combustion processes and so on, smaller particles are generated. Smaller particles that can then get into your lungs. Even smaller particles can get into the smallest components of your lungs, the alveoli. And even smaller particles can actually are that small that they can pass through the cell walls. They get into your blood, and because your blood goes everywhere, the particles also go everywhere. And indeed, post-mortem research has indicated, has found metal particles in the brain of people. And then, of course, these particles are not supposed to be there. And that's also why particulate matter has been linked to all kinds of diseases, including Parkinson and Alzheimer's disease. So this is something we need to take care of. And we get a lot of these particles, certainly in cities where there's a lot of traffic. And we worked here together with the company ENS Technology, and they manufacture actually, you could call them large air cleaners by electrostatic precipitation. So what does it mean? You charge the particles with a positive charge in this case, and then the particles are attracted to a grounded plate, and there they are collected. And when you keep the system running, for example, in a parking garage where high concentrations can occur, the metal plate where the particles are collected will first be gray, but over the course of days it will become dark gray, and then it will become black. And finally, when you rinse all this coagulated particulate matter off the plate, and you get something as shown here in this graph. So this is particulate matter coagulated. It's pitch black. And if you rub it into your hands, it will take you quite a while to wash it off again with lots of soap. And you have to imagine that this is what we are inhaling. Well, not this amount, of course, and certainly not on a daily basis, but this is something that is of concern. And the World Health Organization finds this the most problematic and most carcinogenous air pollutant. So we need to take care of that. What we did here actually was a nice idea by this company, ENS Technology, to put this kind of air cleaners in parking garages where a lot of particulate matter is generated, and then actually to try to first, of course, clean the air inside, but also to have an effect on the outdoor environment. Because otherwise, when we ventilate the parking garage, we just flush the particulate matter back into the open, and then we move the problem to outside. So also here we made a large computational grid of Eindhoven city center at the whole park inside the circular road around the city. So you can see here that some buildings, of course, were simplified a bit, but the main shapes important for aerodynamics are present. Sometimes simplification was maybe a bit less polite. So here we were a bit less respectful towards the church, but in good Christian tradition, I hope that they will forgive us for that, for the sake of grid quality. Here you see some ventilation openings of specific parking garages. So a lot of dedication was made to modeling these underground parking garages and then the air cleaners inside. And then we had two cases, well, three cases actually. One was a scenario as it was, so without air cleaners and parking garages. One was with 99 units spread over a part of the city center. And the other case was almost 600 units spread over the same area. Also here, steady run simulations, reliable K-epsilon model, so nothing too fancy, but also validated with wind tunnel measurements. And then finally here some results. So what you can see here is contours of particulate matter, PM10, in a horizontal plane at 1.75 meter height, so pedestrian height. On the left side, without these air cleaners. And then you can see that where there is an exit of a parking garage and the particulate matter is being flushed out, you see higher concentrations, of course. With these removal units, you can actually really reduce that quite significantly. In some cases, better than others. Here, for example, you see this large spot of concentrations here, which is completely removed after engagement of these 600 units. And here, finally, what you see here is the reduction in PM10 that we get in the city center, some parts of the city center, due to these, on the left side, 99 units, and on the right side, almost 600. So these reductions are significant. They are not massive. If you see this dark blue color, that is, I think, about 10% reduction. And you might argue, okay, that's not a lot. But it has been repeatedly shown, demonstrated, and published in medical journals that even if you reduce particulate matter concentration a little bit, this already can be translated in less morbidity, less mortality, and so on. So these concentrations, no matter how small they are, these reductions, they can be important. Then the same actually was done in New Delhi, where I think all of us know that particulate matter concentrations and air pollution is really a big issue. And here we focused on the American Embassy School, together with our partners in this project. And that's actually a school with a courtyard, as you can see here. And the ventilation of these rooms, the classrooms, where the children are present for a large part of the day, is the air from the ventilation is taken from the courtyard. So our thought was, okay, this courtyard is partly enclosed. If we can purify the air inside this courtyard, then of course also the air going into the schools will be cleaner, and that will be healthier for these kids. And indeed, that was also done. Measurements were made, computer simulations were made actually before that in order to decide how many systems we needed and where. So this kind of large units were installed. Again, steady run simulations, because we can always apply more complicated simulations, but as sometimes said, a model should be as complex as needed, but not any more complex than that. So steady runs here after validation proved to be certainly sufficient. And here you see reductions in PM2.5 concentrations inside these courtyards. And here we get reductions at locations with up to 40%. So that's, of course, a big improvement. And the system has now also been implemented, has been tested, measured, and with good results over there. And our PhD student Rob Vervoort, who did the computational study together with us, also published an article about this. Right, a bit different application is wind comfort at terraces of a high-rise building. There's not that much information about wind comfort on terraces, but it is an issue because certainly for high-rise buildings, high wind speed can occur there. And at some point we were contacted by an architectural and engineering company, ELD Partnership, who had made actually quite special design of a building facade. So it's a facade, but then there's a second facade, and the second facade is partly open, partly closed, with this kind of checkerboard pattern that you can see here. And they actually want to get more information about the the wind comfort on these terraces. And so this is of course also something that should be studied with CFD, because if you put that into a wind tunnel, you scale it down, then your details will become so small that your flow that is in reality turbulent might become laminar. So that's really again a case that where simulation needs to be engaged. So this park tower in Antwerp is shown here in red on the top figure, and then you see in the mesh and this black area here. And yeah, that's because the cell resolution had to be quite high there, because we had to model all these components in this checkerboard pattern. And what you get finally, if you run these simulations, again, steady run simulations. So again, yeah, the workhorse of industrial CFD in action. And this is an example of what we call the amplification factor in a horizontal plane, with the wind direction as indicated here, where yellow and red are indicating high velocities, and blue lower velocities. And yeah, it takes some focus here, but if you can see this line here, which is green yellowish, and you compare that with the same area here you actually get larger velocities. And you can see that a bit more clearly if you look at it from a top view. This is again this amplification factor, so that's actually a dimensionless wind speed. Here you see quite high velocity, certainly on this side. But if you focus actually on the area of the terrace between the first facade and this checkerboard facade, you see actually that there's some kind of pressure equalization occurring there that leads also to lower velocities. So actually this idea of this checkerboard pattern is a very good idea by these designers, and it's really a situation that and a solution that helps to improve the wind comfort on these terraces. These days, there is quite some attention to heat stress in cities. And there's a reason for that, of course, because it is expected that heat waves will happen more frequently and they will be more intensive. And this, of course, also has impacts on the health and the comfort of people, and also on building energy consumption, and certainly when we are thinking about active cooling. So different phenomena, physical phenomena are involved here. Of course, the reduction of wind speed, but also the amplification of shortwave radiation gain, the lack of vegetation and water ponds or water surfaces in urban areas. And sometimes this is also referred to as the urban heat island effect, and the fact that inside an urban area temperatures can be substantially higher than in the surrounding rural area. So this is also an example where CFD can be engaged. So we did it actually here for a district in Rotterdam, where the task was to think about climate adaptation measures. So actually to be able to reduce the heat waves inside this area. So this is part of the computational domain. You also see the computational grid there. And we focused on actually a heat wave. 2006 was a period where actually many people in Western Europe died because of this heat wave. And you can actually then model with CFD how your temperature, surface temperatures, air temperatures change over a period of several days. And this is an example of surface temperatures here. This is in the morning, 5 o'clock, when you see that the buildings are in light blue are still a bit warmer than the surrounding ground area. Then the sun comes up, of course, starts heating the buildings, heat is being accumulated. That increases over the course of the day. And then finally, when the sun goes down and nocturnal radiation sets in, you get actually the same cycle starting again. Okay, that looks maybe not too unrealistic, but of course it's important to compare that with measurements. So here we used satellite imagery observations of surface temperatures, and we compared that with the CFD simulation. So the measurements are the black dots, the CFD simulations are the pink dots. So surface temperature on the vertical axis, time in hours on the horizontal axis of 5 days. And overall, you see that this day and night cycle is reproduced quite well. Here we have some deviations, and the reason for that probably is that in the CFD simulations we don't work with clouds, with cloud covers. And even in our heat waves, Netherlands and Belgium are not famous for their fantastic weather. Even in heat waves we have some clouds sometimes, and that of course is something that you will also see reflected in the measurements and not necessarily in the simulations. So the fact that we can actually predict heat waves and predict the temperature, surface temperatures, air temperatures also means that we can start predicting what adaptation measures can yield. And a typical adaptation measure that is often mentioned is painting roofs and maybe also facades of buildings white so that there is more reflection of sunlight and less absorption. And this was also an exercise that we performed here. And yeah, depending on the increase actually of this shortwave reflectivity, you can see here at the bottom, these are again different scenarios, that this can actually gain you a few degrees in terms of surface temperature, and not only for one building, but actually for the whole area if you would apply this reflectivity to all these places. And then there's also something that we tested, and it looks maybe a bit uncommon, and it is for many parts of the world still a bit uncommon, but mist spraying is something that is being used, increasingly being used, and what you actually get is very small droplets that are released into the air. Well, water needs a lot of energy to evaporate, so this actually extracts the heat from the air and can cool the air down substantially. So this is actually a evaporative cooling system that is used in several countries. Okay, different type of application now as we move towards the end of this presentation. At some point, actually, we were asked by ARU, which is a company of cycling gear, to help them in designing a new race cycle helmet. And well, this is not a run simulation anymore. And here we really needed to take into account the transient effects. And yeah, the interesting thing about a race helmet actually is that to make it as aerodynamic as possible, or to make it as fast as possible, you should actually find a compromise between the air going over the helmet and the air going through the helmet, so beneath the helmet and the head of the person. And the latter is also used for ventilation. So actually what we found here, what was really important in this design, and it's something that we saw clearly from the simulations, is that if you would have a completely closed helmet, then here there would be actually behind, above the neck of the cyclist, there would be a large underpressure area, and that would cause a suction force that of course is not beneficial for the cyclist. And if you guide a sufficient amount of air through the helmet, then actually this amount of air coming out of here will actually reduce this suction. So you really have to try to somehow fill up this gap with some of the ventilation air going through this helmet. And this actually was an iterative design process that we did together with the company to arrive at the new helmet. And then finally they made a movie of that. I'll just very briefly play that for you. Where you also see part of the simulations coming back, and you see here the opening. Also in wind tunnel testing, you could actually see the same effect. And then this amount or this type of balancing of the flow and some other details are sometimes details that you wouldn't think about when you see a helmet, and that would be important for aerodynamics, but it's really good to apply simulation to see things that sometimes also we would not expect to act in a given way. Here I will not spend too much time here. We have been working with Lapierre, and we're still working with them again now for designing a new race bicycle. That's also done with with CFD, almost exclusively with CFD actually. And yeah, there's a lot of details that are being focused on here. So yeah, requires a lot of computational cells, but yeah, I get very valuable insights there, and it's a bit complicated always because you have to, yeah, you have all these different tubes and all these different components that are impacting each other. And when you get a gain on one tube, it might be a disadvantage on the other tube and so on. So that is a intensive iterative process. There's also a movie of that made here, but it's it's without sound here, so I will not bother you with that. I will go to the last part of the presentation, and this was actually a project that was a lot of fun. When we test cyclists, we often do that in the wind tunnel, but sometimes it's very practical to do that in the wind tunnel. So this is Lotto NL Jumbo, as the team was called in 2017. And yeah, I think that many of you know that at that moment it was so-called ugly duckling in the peloton. It was one of the weakest teams. But yeah, today it has become, I think, a beautiful swan. So it's now really a top team, and that has, of course, a lot to do with the fantastic riders that they are there, but also with all the people taking care of this team in a very dedicated way, and also a little bit due to our aerodynamics input. So at some point we were asked by Mathieu Heijboer, the performance manager of Jumbo-Visma, to work towards an optimized team time trial sequence for the 2019 Tour de France. Because if you have 8 riders and they're riding in a time trial in a certain sequence, well, you have actually 8 faculty number of sequences, so that's 40,320. And you can imagine that we cannot test 40,320 sequences in the wind tunnel. Well, actually also not with CFD, but at least you can test or you can calculate a few. And there were a few specific orders where Mathieu Heijboer wanted to have the result, and indeed some of these orders are much faster overall than others, and it's very difficult to do that just based on intuition. So we calculated that for the team, and then finally an optimized order came out of that, and that actually was well, I think one of the races that I've been watching where I was most nervous, but yeah, I think the team did a fantastic performance there, and they beat Ineos with 20 seconds. And Ineos also was widely known as the best team of the world at that moment. So that's really really nice. And of course, this optimized order, optimized sequence is just one piece of the whole puzzle. Because as researchers, I always say we have to be modest. You contribute a very little bit to this kind of achievement, because the biggest piece of the puzzle, of course, are the riders and all the other aspects that go along with that. But it's it's very nice then afterwards to see the joy of these guys, and I really have to thank Mathieu Heijboer here. We've been working together already with him for 5 years now, and it's always very enjoyable and very pleasant. Conclusions. Well, what I wanted to show here by showing you a number of different applications is how important computer simulation, CFD, has been in each of these applications. And we've always used a little bit of measurements, but measurements are often very time consuming, and you can only do them for a few configurations, but we need them for the validation, and then you can use computer simulation and really explore the physics of a given problem. And also that even though this certainly in academic communities often quite some criticism about RAN simulations, still if you do a RAN simulation in a good way with a good resolution grid, with a good solver, you can get very accurate results, and often results that are accurate enough to make the decisions that you want to make. And so because all these first 6 applications were done with RAN simulations. So I also recently wrote an article about that to indicate that it's not always required to go to scale resolving simulations. Sometimes yes, but not always. And we should not make our method more complicated than it needs to be. Finally, I want to thank all of you for your time and your interest in this webinar and in this presentation. And I would like to thank Jerry, Adrian, Jan, and Erna for the kind invitation to give a presentation here. Thank you very much.
Thank you, Professor. Thank you very much for this really nice, interesting webinar with all kinds of slides. I will now hand over to you, Adrian, to go to the last slides.
Yes, and thank you very much, Professor Blokke. I think it was a very nice, interesting, very nice set of use cases, and I really liked the humorous touches as well. Let's see if I can move to the next slide. Doesn't work. Maybe can you move to the next slide, Erna?
Yes, of course, no problem.
Okay. So before I move to the final slide, I'm already making a shout out to our next online event, which will be a webinar focused on robust product optimization with our Ansys OptiSlang solution. It will be the 28th of June, and you see some of the applications that will be covered here. You will all receive a copy of the slide deck, so when you get that, you can also click here. Obviously, if you click now, it will not work, but then you will come on the landing page. If you are interested, you can register yourself. Next slide, please. So with that, I think we are at the end of this webinar. I see we have 7 minutes left, so if there are questions, we are happy to take them. Feel free to unmute yourself or drop it in the chat box. Otherwise, you can also see our contact details on slide, or you could see them. If you can, maybe can come back one slide, Erna.
Sure, no problem.
Our contact details are on the slide. So if you say, hey, that were really interesting cases, we are working on something, we are interested in CFD or looking at a particular problem, how we could leverage CFD, of course, feel free to contact us, and we'll be happy to be in touch with you and discuss further. Erna, looking at you, are there questions?
Yes. I will have a look. For now, there are no questions. I have all unmuted you all, so you can unmute yourself. If you have any questions, please drop them in the question or in the chat box, then we can answer. Are there any questions? Please let us know. Otherwise, we will wait. No questions for now, no problem at all. But for now, thank you for attending today's webinar. And please do not hesitate. You also see the contact details on this slide, share with you with the recording after this webinar. On behalf of Professor Blokke, Adrian and I, and of course of Team Infinite, but also Ansys, we would like to thank you for joining us today and wish you a very nice afternoon. Thank you very much. Bye-bye.
Thank you, everyone. Goodbye.
Bye-bye.
Goodbye, everybody.